on the 17th of February, in the year 1600, in a public square in Rome called the Campo de' Fiori. A crowd gathered to watch a man die. His name was Giordano Bruno. He was a former monk, a wandering philosopher, and by the standards of his age, a dangerous heretic. For 8 years, the Roman Inquisition had held him in a dungeon, demanding he take back the ideas he had written in books that scandalized the church. He refused, and so they brought him to the square, stripped him, tied him to a wooden stake, and set him on fire. What had Bruno said that was so threatening? Among his many offenses, one stands out as eerily modern. Bruno declared that the universe was infinite, that the stars were distant suns, each one orbited by its own worlds, that there was no center, no edge, no boundary to creation, and most dangerously of all, he insisted that there were innumerable worlds out there beyond our own, perhaps even inhabited by other beings. 426 years later, some of the most brilliant physicists alive are saying something remarkably similar, not as poetry or philosophy, but as a consequence of our deepest and most rigorously tested theories of nature. They are telling us that our universe, this entire cosmos of 2 trillion galaxies and hundreds of billions of light years of space, may be nothing more than a single bubble in an unimaginably vast ocean of other universes. That reality itself may be far, far larger than anything we can see or touch or measure. That we may, in fact, be one of infinite realities. This is the idea of the multiverse, and it is one of the most mind-bending, controversial, and genuinely profound ideas in all of science. Tonight, we are going to take a long, slow journey through this idea. We are going to trace its roots all the way back to the birth of quantum mechanics, when physicists first discovered that reality, at its most fundamental level, does not behave the way anyone expected. We will follow a quiet, troubled graduate student named Hugh Everett as he proposed one of the most radical ideas in the history of physics, and watched it get ignored for decades. We will explore the explosive theory of cosmic inflation and how it implies that our universe may be just one pocket in an eternally expanding sea of space. We will wade into the strange mathematics of string theory, where the hidden geometry of tiny, curled-up dimensions could give rise to more possible universes than there are atoms in all of observable creation. We will wrestle with the eerie fine-tuning of our universe, the way certain numbers in physics seem almost impossibly calibrated to allow for the existence of stars, planets, and life. And we will confront the deepest question the multiverse raises. Is this even science anymore? Or have we drifted into something else entirely? So settle in. Let the room get quiet, because the story of the multiverse is the story of everything we think we know about reality, pushed to its absolute limit. And it begins with a beam of light, a pair of slits, and a mystery that has haunted physics for more than 2 centuries. But first, a bit more about the history of this idea, because Bruno was not entirely alone. The notion that our world might not be the only one stretches back to the ancient Greeks. In the 5th century before the Common Era, the philosopher Democritus, the same thinker who proposed that all matter is made of indivisible atoms, also argued for the existence of infinite worlds. He imagined an endless void in which countless clusters of atoms swirled together to form countless cosmoses, some with suns and moons, others barren and empty. His student Epicurus carried the idea further, and the Roman poet Lucretius gave it eloquent expression in his poem on the nature of things, writing that it is in the highest degree unlikely that this earth and sky are the only ones to have been created. For more than 1,000 years after the fall of Rome, the idea was suppressed by Christian orthodoxy, which held that God created one universe, centered on one earth, for one species made in his image. The doctrine of a single, finite cosmos was not merely a scientific position. It was theological. To suggest otherwise was to challenge the very structure of creation. And then came Bruno, striding onto the stage of history with the confidence of a man who believed he had glimpsed the truth, and the stubbornness of one who would not pretend otherwise. He had read Copernicus, who had placed the sun at the center of the solar system, and he had taken the idea much further than Copernicus himself ever dared. If the Earth is not the center of everything, Bruno reasoned, then perhaps the sun is not either. Perhaps the sun is just one star among many, and those other stars have their own planets, and perhaps some of those planets harbor life. Perhaps the universe has no center at all. Perhaps it is infinite. Bruno wandered Europe for years, from Italy to France to England to Germany, teaching, writing, debating, and making enemies everywhere he went. He was brilliant, argumentative, and utterly uncompromising. When the Inquisition finally caught up with him, they offered him the chance to recant. He refused, and they killed him for it. Today, a bronze statue of Bruno stands in the Campo de' Fiori, on the spot where he was burned. He faces the Vatican with an expression that might be defiance or might be sorrow. Below the statue is an inscription from his admirers, placed there in the 19th century. It reads, "To Bruno, from the century he foresaw." He could not have foreseen quantum mechanics or inflationary cosmology. He could not have imagined string theory or the simulation hypothesis, but the fundamental question he was asking, whether our world is the only one, is exactly the question that modern physics has found itself forced to confront. And the answers that are emerging are stranger and more magnificent than anything even Bruno could have dreamed. So let us begin at the beginning of the modern story, with a beam of light, a pair of slits, and a mystery that changed everything. In 1801, a British polymath named Thomas Young performed an experiment so simple that you could set it up on a kitchen table, and so profound that it would eventually help overthrow our understanding of reality. Young was not a specialist. He was a physician, a linguist who helped decipher the Rosetta Stone, and a natural philosopher in the grand tradition of the Enlightenment. His interests ranged from the mechanics of the human eye to the elasticity of materials to the behavior of light, and it was light that would bring him his most enduring fame. Young took a beam of sunlight and directed it toward a screen with two narrow, parallel slits cut into it. Behind the screen, he placed a second surface where the light could land and be observed. If light were made of tiny particles, like little bullets fired from a gun, you would expect to see two bright strips on the back surface, one behind each slit, like paint sprayed through a stencil. But that is not what Young saw. Instead, he observed a pattern of alternating bright and dark bands spreading across the surface, a pattern that could only be explained if light was behaving as a wave. When two waves overlap, their peaks can reinforce each other, creating brighter regions or cancel each other out, creating dark bands. This is called interference, and it is a signature behavior of waves, whether they are ripples on a pond or vibrations in a guitar string. Young's experiment seemed to settle an old debate. Isaac Newton believed light was a stream of particles. Christian Huygens had argued it was a wave. Young's double-slit experiment appeared to prove Huygens right. Light was a wave. Case closed. Except it was not closed. Not even close. A little over a century later, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would unravel everything. Albert Einstein, analyzing a phenomenon called the photoelectric effect, in which light knocks electrons off a metal surface, showed that light could not be purely a wave. To explain the experimental results, light had to come in discrete packets of energy. These packets would later be called photons. Light, Einstein argued, was also a particle. This was deeply strange. How could light be both a wave and a particle? The double-slit experiment showed wave behavior. The photoelectric effect showed particle behavior. Which was it? The answer turned out to be far weirder than anyone imagined. In the decades that followed, physicists discovered that if you send individual photons, one at a time, through the double slits, each photon lands on the detector as a single point, like a tiny bullet. But if you keep firing photons, one after another, and record where each one lands, something astonishing happens. Over time, the individual points accumulate into the same wave-like interference pattern Young had observed. Each photon, traveling alone with nothing else to interfere with, somehow produces a pattern that should only be possible if it were passing through both slits simultaneously, interfering with itself. Let that sink in for a moment. A single particle, a single indivisible unit of light, appears to take two paths at once. It passes through both openings as though it were a wave spread across space, and yet it arrives at the detector as a single point, like a particle striking a target. It is as if each photon explores every possible route through the experiment at the same time, and only commits to a single outcome at the very last moment when it is detected. This is not a matter of the photons splitting in half. Photons do not split. If you place detectors at each slit and watch carefully, you will find that each photon goes through one slit or the other, never both. But when you do that, when you watch, the interference pattern disappears. It is as if the photon knows it is being observed and changes its behavior accordingly. Physicists have spent decades trying to find loopholes in this result, and they have failed. Delayed choice experiments, in which the decision to observe is made after the photon has already passed through the slits, produce the same result. The very act of gaining information about which path the photon took, even in principle, even after the fact, eliminates the wave-like interference. The physicist John Archibald Wheeler, who would later play a crucial role in the story of the multiverse, described this with a vivid image. He imagined the photon as a great smoky dragon. Its tail is visible at the source, where it is emitted. Its mouth is visible at the detector, where it is absorbed. But in between, the body of the dragon is wreathed in smoke, and you can see nothing. The photon's journey between emission and detection is fundamentally unknowable, not because our instruments are too crude, but because the knowledge does not exist. Reality itself is undefined between measurements. And here is the part that still makes physicists uneasy, even after 100 years. If you try to catch the photon in the act, if you place a detector at the slits to determine which one the photon actually goes through, the interference pattern vanishes. The photon behaves like a normal particle, going through one slit or the other, never both. The mere act of observing which path the photon takes destroys the wave-like behavior that creates the pattern. This was not a quirk of photons alone. In the 1920s and 30s, experiments showed that electrons, neutrons, and even entire atoms exhibited the same bizarre duality. Matter itself, the stuff that makes up you and me and everything we can touch, behaves as both particle and wave, depending on how you look at it. Richard Feynman, one of the greatest physicists of the 20th century, once said of this experiment that it contains the only mystery of quantum mechanics. Everything else, he implied, is just a variation on this one baffling theme. And it was in trying to make sense of this mystery that physicists split into camps, launching debates that persist to this day, and opening the door, whether they intended to or not, to the idea of parallel universes. To understand why the double-slit experiment matters so much, you have to appreciate what it implies about the nature of reality itself. In our everyday experience, things have definite properties. Baseball is either here or there. A coin is either heads or tails. A door is either open or closed. But at the quantum level, none of this holds. A particle does not have a definite position until something forces it to choose one. Before that moment, it exists in a kind of limbo, a haze of possibility, all of its potential states coexisting simultaneously. This is not a limitation of our knowledge. It is not that the particle has a definite position, and we simply do not know what it is. The mathematics of quantum mechanics is very clear on this point. The particle genuinely does not have a definite position. It has a probability distribution, a spread of possibilities, each one weighted by a number called an amplitude. This probability distribution is encoded in the wave function, a mathematical object that contains everything there is to know about a quantum system. The wave function is not a physical wave in the ordinary sense. It does not ripple through water or air. It exists in an abstract mathematical space, but its effects are profoundly real. It determines the probabilities of every possible measurement outcome. It governs the behavior of every atom, every molecule, every particle of light. It is, in a very real sense, the fundamental description of reality at the deepest level we have been able to probe. And the central question, the question that would eventually lead to the idea of parallel universes, is this: what happens to the wave function when a measurement is made? The first serious attempt to interpret the strangeness of quantum mechanics came from the city of Copenhagen and from the towering intellect of a Danish physicist named Niels Bohr in the mid-1920s. Bohr and his colleagues, most notably the German physicist Werner Heisenberg, developed a framework for understanding quantum behavior that would become known as the Copenhagen interpretation. It remains, even now, the most widely taught version of quantum mechanics in universities around the world. The Copenhagen interpretation says something simple on the surface, but profoundly unsettling underneath. It says that a quantum system, say an electron or a photon, does not have definite properties until it is measured. Before measurement, the system exists in what is called a superposition, a kind of mathematical cloud of possibilities. An electron does not have a specific location. Instead, it has a range of possible locations, each with a certain probability. These probabilities are described by a mathematical object called the wave function, developed by the Austrian physicist Erwin Schrödinger in 1926. The wave function is a beautiful and precise tool. It tells you, for any given measurement, the probability of each possible outcome. It evolves smoothly and predictably according to the Schrödinger equation, which is as deterministic and well-behaved as Newton's laws of motion. If you know the wave function at one moment, you can calculate what it will be at any future moment. There is no randomness in the equation itself. But according to the Copenhagen interpretation, when you actually perform the measurement, when you look at the electron and determine where it is, the wave function collapses. All those other possibilities vanish, and the system snaps into a single, definite state. This collapse is sudden, random, and irreversible. It is not described by the Schrödinger equation. It is an additional postulate, bolted on to the theory by hand. And here is the problem that would eventually give birth to the many worlds interpretation. The Copenhagen view draws a sharp line between the quantum world and the classical world. On one side of the line are atoms and electrons, described by wave functions and superpositions. On the other side are measuring devices, laboratories, scientists, and cats, all described by ordinary, everyday, classical physics. But where exactly is the line? Who or what constitutes an observer? Does the measuring device have to be conscious? Does it have to be large? The theory does not say. And this ambiguity troubled a great many people. This is the heart of the measurement problem. And it bothered a lot of people, including Schrödinger himself. In 1935, he devised a thought experiment to illustrate just how absurd the Copenhagen interpretation could become when pushed to its logical extreme. Imagine, he said, a cat sealed inside a steel box. Inside the box is a tiny amount of radioactive material, a Geiger counter, and a vial of poison. If a single atom of the radioactive material decays, the Geiger counter detects it and triggers a mechanism that shatters the vial, releasing the poison and killing the cat. Now, radioactive decay is a quantum process. According to quantum mechanics, until the atom is observed, it exists in a superposition of decayed and not decayed. And since the cat's fate is linked to the atom's state, the Copenhagen interpretation implies that the cat, too, is in a superposition, simultaneously alive and dead. Only when someone opens the box and looks does the wave function collapse, and the cat becomes definitively one or the other. Schrödinger intended this as a reductio ad absurdum, a demonstration that something must be wrong with how we were interpreting the math. Cats are not simultaneously alive and dead. That is absurd. But the equations of quantum mechanics do not draw a line between the microscopic world of atoms and the macroscopic world of cats and people. The math applies everywhere. So where does superposition end and ordinary reality begin? This is sometimes called the measurement problem, and it is widely regarded as the deepest conceptual puzzle in all of physics. It is not a problem with mathematics. The equations work perfectly. It is a problem with what mathematics means, and it has no universally accepted solution. Some physicists, following Bohr, say that the question is meaningless, that quantum mechanics is a tool for predicting the results of experiments, not a description of what is really going on at the deepest level. Shut up and calculate, as the famous saying goes. Others, like the physicist Roger Penrose, believe that there is something missing from quantum mechanics, some additional physical process, perhaps related to gravity, that causes the wave function to collapse objectively, regardless of whether anyone is watching. Still others, like the advocates of the de Broglie-Bohm pilot wave theory, believe that particles always have definite positions, guided by a hidden wave, and that the appearance of randomness is an illusion. And then there is the fourth possibility, the one that a quiet graduate student at Princeton would propose in the 1950s, the one that says the cat is not both alive and dead. Rather, there are two cats, one alive, one dead, each in its own branch of reality. Both are real, both exist. We just cannot see both from where we stand. This question gnawed at physicists for decades. Bohr himself acknowledged that the boundary between the quantum and classical worlds was fuzzy and somewhat arbitrary. Einstein famously declared that God does not play dice, rejecting the notion that the universe was fundamentally probabilistic at its core. Their debates at the Solvay conferences of 1927 and 1930 are legendary, with Einstein devising ever more ingenious thought experiments to challenge quantum mechanics, and Bohr staying up all night to find flaws in Einstein's arguments. But for all the discomfort, the Copenhagen interpretation worked. It gave correct predictions. Physicists could use it to calculate the behavior of atoms, molecules, and subatomic particles with stunning accuracy. Quantum mechanics became the most successful predictive theory in the history of science. And most physicists, following the practical advice often attributed to the era, learned to shut up and calculate. Most physicists, but not all, the Bohr-Einstein debates deserve a moment of our attention because they shaped the philosophical landscape from which the multiverse would eventually emerge. At the 1927 Solvay conference in Brussels, the most famous gathering of physicists in history, 29 of the world's greatest minds sat around a table to discuss the new quantum theory. 17 of them were or would become Nobel Prize winners. A photograph from that conference shows them all: Einstein, Bohr, Heisenberg, Schrödinger, Planck, Curie, Dirac, Born, Pauli, and others. It is one of the most extraordinary concentrations of intellectual power ever assembled in one room. Einstein and Bohr were the central figures. Einstein kept devising thought experiments designed to show that quantum mechanics was incomplete, that there had to be some deeper reality beneath the probabilistic surface. At one point, he proposed an experiment involving a clock and a box of photons, designed to violate the uncertainty principle. Bohr stayed up all night analyzing the argument, and by morning had found the flaw. Ironically, he used Einstein's own general theory of relativity to do it. The debates continued through the 1930 Solvay conference and beyond. Einstein never accepted the Copenhagen interpretation. In 1935, he and two collaborators, Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics could not be a complete description of reality. Their argument, now famous as the EPR paradox, involved a phenomenon that Einstein dismissively called spooky action at a distance. What we now know as quantum entanglement. The EPR paper did not destroy quantum mechanics, but it sharpened the philosophical stakes enormously. These debates mattered because they framed the question that would eventually lead Hugh Everett to his revolutionary idea. If quantum mechanics is correct, and if the wave function is real, then what actually happens when we make a measurement? Does the wave function really collapse, or is something else going on? Because in a dormitory at Princeton University, in the autumn of 1954, a young graduate student was drinking sherry with a friend and thinking about quantum mechanics. And what he was thinking would change everything. His name was Hugh Everett III. He was born in 1930 in Washington, D.C., raised mostly by his father and stepmother, and by all accounts was brilliant from an early age. He earned a degree in chemical engineering from the Catholic University of America before receiving a fellowship to pursue graduate studies at Princeton, one of the great centers of theoretical physics in the world. It was there, under the supervision of the legendary John Archibald Wheeler, that Everett would develop what is arguably the most audacious interpretation of quantum mechanics ever proposed. Everett was a curious figure. He was enormously intelligent, but socially reserved. The kind of person who could sit through a party without saying a word and then later write a paper that would shake the foundations of physics. He had a dry sense of humor and a fondness for science fiction, a genre that would later repay the favor by drawing endless inspiration from his work. Peter Bion, who wrote a biography of Everett, described him as someone who lived almost entirely in his own head, a man more comfortable with equations than with people. The story, as it is often told, began on that sherry-fueled evening in 1954. Everett was talking with his friend Charles Misner, another graduate student, about the absurdities of the Copenhagen interpretation. Why, Everett wondered, do we need this special rule about wave function collapse at all? The equations of quantum mechanics, the Schrödinger equation in particular, describe how quantum systems evolve over time. These equations are smooth, continuous, and deterministic. Nowhere in them is there a mechanism for collapse. The collapse was something Bohr and his colleagues had bolted on to explain why we only see one outcome when we make a measurement, but the equations themselves did not require it. What if, Everett asked, we just took the math at face value? What if we removed the collapse postulate entirely and let the Schrödinger equation apply universally to everything, including measuring instruments, observers, and yes, even cats? The answer was staggering. If you do this, then when a measurement is made, the wave function does not collapse into a single outcome. Instead, it evolves into a superposition that includes all possible outcomes simultaneously. The observer becomes entangled with the system being observed. If the electron can be in location A or location B, then after measurement, the universe evolves into a state where one version of the observer sees the electron at A, and another version sees it at B. Both outcomes occur. Both are real. In Everett's picture, the universe does not choose. It splits, or more precisely, it branches. Every quantum event that has multiple possible outcomes gives rise to multiple branches of reality, each one containing a version of the world in which a different outcome occurred. The cat is alive in one branch and dead in another. The photon goes through the left slit in one branch and the right slit in another. Every possibility allowed by quantum mechanics is realized somewhere. Everett originally called this the relative state formulation. It was later named the many worlds interpretation by physicist Bryce DeWitt, who did more than anyone to popularize the idea. Everett himself compared the branching to an amoeba splitting into daughter cells. Before the split, there is one history. After the split, there are two, each carrying an identical memory of the past, but diverging into different futures. It is worth emphasizing what Everett was not saying. He was not saying that the universe literally cracks in half every time an electron does something. The branching is not a physical splitting of matter and energy. It is a branching of the wave function, a mathematical object that describes the state of the entire universe. The branches do not communicate or interact. From within any single branch, everything looks perfectly normal. You make a measurement, you get a result, and you go on with your day. You have no idea that another version of you in another branch got a different result and went on with a different day. The mathematical beauty of this idea is that it preserves the fundamental linearity of quantum mechanics. The Schrödinger equation is a linear equation, which means that if two solutions are possible, then any combination of those solutions is also a possible solution. The Copenhagen interpretation breaks this linearity by introducing collapse, a sudden, nonlinear jump from many possibilities to one. Everett's interpretation preserves linearity by keeping all the possibilities in play forever. To say this idea was not well received would be an understatement. Everett completed his thesis in 1957, and Wheeler, who had encouraged mathematical development, nevertheless pressed Everett to tone down the more provocative language. The published version was significantly shorter than Everett's original draft. Niels Bohr, when he heard about it, was dismissive. Most physicists either ignored it or regarded it as outlandish speculation. Wheeler took Everett to Copenhagen to meet Bohr in person, hoping to broker a dialogue. The visit did not go well. Bohr and his associates showed little interest in Everett's ideas. Years later, one of Bohr's students, Oj Peterson, reportedly told Everett that the problem with his theory was that it was theology. The conversation between Bohr and Everett was described as a total failure of communication. Two brilliant minds talking completely past each other. Everett, frustrated and disillusioned, left academic physics entirely. He went to work as a defense analyst for the Pentagon, applying mathematical optimization techniques to nuclear war planning. He became successful and wealthy, founding a consulting company that worked on classified military projects. But he never returned to physics, and by most accounts, the rejection of his life's most important work left a deep mark. He became a heavy drinker and chain smoker. He was emotionally distant from his family. His son Mark, who would later become the lead singer of the rock band Eels, wrote and spoke movingly about his father's absence and eventual death. Hugh Everett III died in 1982 at just 51 years of age, of a heart attack, never knowing that his once mocked idea would gradually become one of the most debated and, in certain circles, most respected interpretations of quantum mechanics. His story is one of the great tragedies of modern physics. A brilliant mind, a revolutionary idea, and a life that ended too soon in obscurity and unhappiness. But the idea survived. In 1970, DeWitt published an influential article promoting the many worlds view. In 1973, he edited a collection of papers that included the full, uncut version of Everett's thesis. Slowly, the idea gained traction. David Deutsch, a physicist at Oxford, became one of its most vocal champions. He argued that the existence of quantum computers, machines that perform calculations across multiple quantum states simultaneously, was itself evidence for the reality of many worlds. If a quantum computer can factor a large number faster than any classical computer, Deutsch asked, where is the computation being done? His answer: in the other branches of the multiverse. In 1977, Wheeler organized a workshop at the University of Texas, and he persuaded Everett to attend and present his ideas. It was the only time Everett ever presented his work to a large audience of physicists. By several accounts, the reception was more positive than Everett expected. But by then, he had been away from physics for too long, and he never came back. Today, the many worlds interpretation is one of the leading contenders among physicists for how to understand quantum mechanics. It is deterministic, it is elegant, and it takes the mathematics of quantum theory seriously without adding extra rules. But it comes at a staggering philosophical cost: the existence of an inconceivable number of parallel realities, branching off from every quantum event, from every radioactive decay, from every photon that strikes a retina, from every chemical reaction in every cell of every living thing. To grasp the scale of what Everett proposed, consider this: a single atom of uranium sitting quietly in a rock undergoes radioactive decay. The quantum wave function describes a superposition of the atom having decayed and not having decayed. According to many worlds, the universe branches. Now multiply that by every atom in the rock, by every atom in the earth, by every atom in every star in every galaxy. The number of branches grows not just exponentially, but hyperexponentially, splitting and splitting again at every quantum interaction, which happens trillions upon trillions of times every second in every cubic centimeter of space. The result is a structure of branching realities so vast, so incomprehensibly enormous, that all the numbers we use to describe large things, the number of stars in the observable universe, the number of grains of sand on every beach on Earth, become laughably inadequate. The many worlds multiverse is not just big, it is a different order of infinity, and yet the branches do not interact. Once they split, they are invisible to each other. You cannot communicate with your other selves. You cannot peek into the branch where you made a different choice. The other worlds are real, according to the theory, but forever inaccessible. The reason for this inaccessibility is a process called quantum decoherence. When a quantum system interacts with its surrounding environment, and every macroscopic system interacts with its environment constantly, the different branches of the wave function lose their ability to interfere with one another. They become, for all practical purposes, separate and independent realities. The quantum coherence that allowed the photon to pass through both slits in the double-slit experiment is destroyed by the flood of environmental interactions. In a fantastically short time, the branches become invisible to each other, like guests at a party who have wandered into different rooms and closed the doors behind them. Each room is real. Each conversation continues, but the guests in one room cannot hear what is being said in the others. This process of decoherence was worked out in detail by physicists in the 1970s and 80s, and it provides the mechanism by which the classical world we experience every day emerges from the underlying quantum reality. It explains why we do not see superpositions of macroscopic objects. The cat interacts with too many particles in its environment. The branches decohere almost instantaneously. This has led some philosophers to ask whether the distinction between real but unobservable and non-existent is meaningful. Supporters of many worlds say yes, because the theory is simpler and more elegant than the alternatives. Critics say that a theory which postulates an infinite number of unobservable universes to avoid a single unexplained phenomenon, the collapse of the wave function, is the very opposite of simplicity. Whatever your philosophical inclinations, the many worlds interpretation has proven remarkably durable. A 2011 poll at an Austrian conference on quantum foundations found it was the second most popular interpretation among physicists, behind only the Copenhagen view. And in the world of quantum computing, where engineers are building machines that exploit superposition to perform calculations impossible for any classical computer, the many worlds picture provides an intuitive framework. When a quantum computer solves a problem that would take a classical computer longer than the age of the universe, the many worlds advocate asks, where is all that computation happening? The answer, in this view, is in the other branches, and quantum branching is just one of several pathways that physics has discovered leading toward the multiverse. Because while Everett was thinking about wave functions at Princeton across the world, other physicists were thinking about the beginning of the universe, and what they found there was, if anything, even more mind-bending. To understand the next kind of multiverse, we need to go back to the very beginning. Not the beginning of human history, or even the beginning of Earth, but the beginning of everything, the Big Bang. For most of the 20th century, the Big Bang model was the prevailing theory of cosmology. It described a universe that began roughly 13.8 billion years ago in an unimaginably hot, dense state, and has been expanding and cooling ever since. In those first moments, the temperature was so high that matter as we know it could not exist. There were no atoms, no molecules, no stars. There was only a searing plasma of elementary particles, a soup of quarks and gluons and photons, so dense that light could not travel more than a tiny distance before being absorbed and re-emitted. As the universe expanded, it cooled. After about 3 minutes, the temperature dropped enough for the first atomic nuclei to form, mostly hydrogen and helium, in a process called Big Bang nucleosynthesis. But the universe was still too hot for complete atoms. Electrons bounced freely between the nuclei, and the whole cosmos was opaque, like a glowing fog. Then, roughly 380,000 years after the Big Bang, the temperature dropped below about 3,000 degrees. electrons were captured by nuclei to form the first neutral atoms. Suddenly, light could travel freely. The universe became transparent for the first time. That first light, released from the plasma like a bird from a cage, has been traveling through space ever since, stretched by the expansion of the universe from its original visible wavelengths into the microwave part of the spectrum. We detect it today as the cosmic microwave background radiation, a faint glow that fills the entire sky, the oldest light in the universe. The evidence for this picture was overwhelming. The observed expansion of galaxies, first measured by Edwin Hubble in 1929. The cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson at Bell Labs, who initially thought the persistent hiss in their radio antenna was caused by pigeon droppings and the abundances of light elements like hydrogen and helium, all matching the predictions of Big Bang nucleosynthesis with remarkable precision. But the Big Bang model, for all its success, had some nagging problems. Why is the universe so flat, so close to the critical density that separates eternal expansion from eventual collapse? The flatness of the universe is like balancing a pencil on its point. Any slight deviation in the early universe would have been amplified over billions of years into a drastically different cosmos. Why is the cosmic microwave background so uniform in temperature, even in regions of the sky so far apart that light could never have traveled between them in the age of the universe? These are called the flatness problem and the horizon problem. And by the late 1970s, they were driving cosmologists slightly crazy. In 1979, a young physicist named Alan Guth, working at Cornell University, proposed a solution so radical it almost seemed like cheating. He called it inflation. The idea was that in the first fraction of a second after the Big Bang, an incomprehensibly tiny fraction, the universe underwent a period of exponential expansion. Space itself stretched faster than the speed of light, doubling in size over and over again in an unimaginably short time. In roughly 10 to the negative 36 seconds, a region smaller than an atom could have expanded to something larger than the observable universe. To put this in perspective, imagine taking a grain of sand and, in a trillionth of a trillionth of a trillionth of a second, stretching it to the size of the observable universe. That is inflation. The numbers involved are so extreme that they resist any attempt at intuitive understanding. They can only be grasped mathematically. Guth arrived at this idea while studying a completely different problem: the overproduction of magnetic monopoles in the early universe. Magnetic monopoles, hypothetical particles carrying a single magnetic charge, were predicted by many theories of particle physics, but none had ever been observed. Guth realized that a period of exponential expansion would dilute these monopoles to undetectable levels, while simultaneously solving the flatness and horizon problems that had been plaguing cosmology. The story of Guth's eureka moment has become one of the great legends of modern physics. Working late one evening in December of 1979, he scrawled in his notebook the now famous words, "Spectacular realization." He understood that inflation was not just a solution to one problem, but to several at once. Inflation solved the flatness and horizon problems in one stroke. The universe appears flat because inflation stretches any initial curvature to imperceptibility, like the surface of a balloon inflated to cosmic proportions. The microwave background is uniform because the entire observable universe originated from a single, tiny patch of space that was in thermal equilibrium before inflation blew it up to colossal size. But Guth's original model had a flaw. The way inflation ended in his version was too abrupt, producing a universe filled with empty bubbles that could not coalesce into the smooth, hot universe we observe. This is called the graceful exit problem, and it was quickly fixed by Andrei Linde in the Soviet Union, and independently by Andreas Albrecht and Paul Steinhardt in the United States. Their revised version, called New Inflation or Slow Roll Inflation, described a smoother transition from the inflationary phase to the normal expansion we see today. Instead of ending in a sudden phase transition, the inflattened field rolls slowly down its potential energy hill, gradually converting its energy into the hot, dense plasma that became the universe we know. The evidence for inflation has grown steadily over the decades. The cosmic microwave background, that faint afterglow of the Big Bang, shows precisely the kind of temperature fluctuations that inflation predicts. These fluctuations, tiny variations of roughly 1 part in 100,000, are believed to be the stretched-out remnants of quantum fluctuations that occurred during the inflationary epoch. They are the seeds from which all the large-scale structure of the universe, galaxies, clusters, filaments, voids, eventually grew. In 2014, a telescope at the South Pole called BICE-Petwo announced the possible detection of primordial gravitational waves in the microwave background, which would have been direct evidence of inflation. The announcement generated enormous excitement, but subsequent analysis showed that the signal was likely caused by dust in our own galaxy. The search continues with more sensitive instruments, but then something unexpected happened. When physicists worked through the mathematics of this improved inflation, they discovered a disturbing feature. Inflation, once started, is extremely difficult to stop everywhere at once. Here is the key insight. Inflation is driven by a quantum field called the inflaton field, which permeates all of space. Think of it as an energy field that fills the universe like an invisible fluid. When this field has a high energy density, it drives exponential expansion. Eventually, the field decays, releasing its energy as hot, ordinary matter and radiation. This is what we experience as the Big Bang, but the decay does not happen everywhere simultaneously. Because the inflaton field is subject to quantum fluctuations, tiny random variations in its energy, some regions of space will see the field decay sooner, while others will continue inflating. And here is the crucial point. The regions that are still inflating are expanding so rapidly that they grow faster than the regions where inflation has ended. Inflation is, in a sense, self-perpetuating. Even as pockets of space stop inflating and become universes, the surrounding inflating space grows so fast that it always dominates. Paul Steinhardt was the first to demonstrate this in 1983. Alexander Vilenkin showed that the phenomenon is generic to essentially all models of inflation. Andrei Linde developed these ideas further in what he called chaotic inflation, or eternal inflation, the picture that emerged was extraordinary. Imagine an infinite ocean of inflating space, stretching out in all directions, expanding at a ferocious rate. Every so often, a tiny region of this ocean transitions out of the inflationary state. It stops expanding exponentially and begins to cool and evolve. Matter forms, atoms coalesce, stars ignite, galaxies assemble. This pocket, this bubble, becomes a universe, our universe, but the ocean surrounding it continues to inflate. And elsewhere in that ocean, other bubbles are constantly forming, each one a separate universe with its own Big Bang, its own history, its own physics. The process never ends. It goes on forever, eternally producing new bubble universes in an ever-expanding sea of inflating space. This is the inflationary multiverse, sometimes called the bubble multiverse, and it is not a speculative add-on to inflationary theory. It is, for most models of inflation, an unavoidable consequence of mathematics. As Guth himself has written, although inflation is generically eternal into the future, it is not eternal into the past. There was a beginning, but there is no end. The multiverse, once started, never stops producing new universes. The image that physicists use to describe this is strangely domestic. They compare it to a block of Swiss cheese or a loaf of bread filled with bubbles. The bread is the eternally inflating space, stretching and expanding forever. The bubbles are the individual universes, the pockets where inflation has ended and ordinary physics has taken over. Our entire observable cosmos, everything from the nearest star to the most distant galaxy, is contained within one such bubble. It is roughly 93 billion light-years across, which sounds enormous until you realize that the inflating space surrounding it is growing faster than light and will never stop. Andrei Lind, the Russian-born physicist who developed many of the key ideas of eternal inflation, once described the picture with characteristic bluntness. He said that if you understand that our universe is just one bubble, then there must be many other bubbles. He compared the instability of inflating space to a drunk person standing on a hill. They can fall in this direction or that direction, and eventually they must fall. Inflation, he said, is the instability of space with respect to its expansion. Once it starts, it simply cannot stop everywhere at once. And each of these bubble universes might be very different from our own. The process by which inflation ends, by which the inflaton field decays, can happen in different ways. These different decay paths can lead to different values of the fundamental constants, different strengths of the forces, different types of particles. In one bubble, gravity might be slightly stronger. In another, the mass of the electron might be different. In yet another, the very fabric of spacetime might have a different number of dimensions, or the forces that hold atoms together might not exist at all. Try to picture it, an ocean of space, expanding exponentially, stretching in all directions forever. Scattered throughout this ocean are bubbles, each one a separate cosmos. In some, stars burn and galaxies spin, and chemistry happens and life emerges. In others, the physics is wrong, and the bubble is nothing but a featureless void, or a blinding plasma, or a space that collapses back on itself before anything interesting can occur. And between the bubbles, the ocean continues to swell, generating new bubbles all the time forever and ever, without end. It is a vision of reality that is simultaneously magnificent and humbling. Magnificent because of its sheer scale and grandeur. Humbling because it reduces our entire cosmos, everything we have ever seen or known or measured, to a single speck in an infinite expanse. We would have no way to detect these other bubbles. They are not just far away in space. They are causally disconnected from us, separated by regions of still inflating space that are expanding faster than light. No signal, no spacecraft, no amount of time would ever allow us to reach them or receive a message from them, or so we thought. But we will return to the question of evidence later. For now, there is another path to the multiverse, one that comes not from cosmology, but from the deepest attempt to understand the fundamental nature of matter itself. String theory is one of the most ambitious intellectual enterprises in the history of science. It is an attempt to do something that has eluded physicists for over a century, to unify all the forces of nature, including gravity, into a single, coherent framework. And it does so by proposing something astonishing about the fundamental structure of reality. To understand why string theory matters for the multiverse, you first need to understand the problem it is trying to solve. In the 20th century, physics developed two spectacularly successful but mutually incompatible theories. General relativity, Einstein's theory of gravity, describes the large-scale structure of the universe. Stars, galaxies, black holes, the expansion of space. Quantum mechanics describes the small-scale structure, atoms, particles, the forces that hold matter together. Both theories have been tested to extraordinary precision. Both are correct, as far as we can tell. But they cannot both be right in their current form, because they contradict each other in extreme situations, like the center of a black hole or the first instant of the Big Bang, where gravity is strong and quantum effects are important. The quest for a theory of quantum gravity, a single framework that encompasses both general relativity and quantum mechanics, is one of the great unsolved problems in physics. And string theory is the leading candidate. In the standard model of particle physics, the most successful theory of the subatomic world, the fundamental building blocks of nature are point-like particles, things with no internal structure and no spatial extent. Electrons, quarks, photons, they are all modeled as dimensionless points. String theory replaces these points with tiny, vibrating strings of energy. These strings are incomprehensibly small, roughly 10 to the negative 35 meters in length, far smaller than any particle we have ever observed. To appreciate this scale, consider that the ratio of a string's length to the width of an atom is roughly the same as the ratio of an atom's width to the diameter of the solar system. These are objects of almost inconceivable smallness. The key insight of string theory is that the different vibration modes of these strings correspond to different particles. Just as a violin string can vibrate at different frequencies to produce different musical notes, a fundamental string can vibrate in different patterns to produce different particles with different masses and charges. In this view, every electron, every quark, every photon is simply a different melody played on the same underlying instrument. The diversity of particles in the universe is not a fundamental fact. It is the consequence of an underlying unity, like the many notes produced by a single vibrating string. The idea has a deeply appealing elegance. Instead of dozens of different types of fundamental particles, each with its own seemingly arbitrary properties, there is just one type of thing, a string. The complexity of the particle world emerges from the simplicity of string vibrations. It is the kind of deep unification that physicists have dreamed about since the days of Einstein. But string theory comes with a catch. For the mathematics to work, for the equations to be self-consistent, the strings cannot vibrate in just 3 spatial dimensions. They require additional dimensions, 6 or 7 more beyond the 3 we experience in the most developed version of the theory, called M-theory, proposed by Edward Witten in 1995, which unified 5 previously separate versions of string theory. Spacetime has 11 dimensions, 10 of space and 1 of time. Where are these extra dimensions? The standard answer is that they are compactified, curled up so tightly at every point in space that they are invisible to us. Imagine a garden hose viewed from a great distance. From far away, it looks like a one-dimensional line. But up close, you can see that it has a second dimension, wrapping around in a circle. The extra dimensions of string theory are like that circular cross-section, but in 6 or 7 dimensions, and curled up to a size far smaller than anything we can probe with current technology. Now, here is where it gets relevant to the multiverse. The geometry of these extra dimensions, the specific way they are curled up, determines the physics we observe in the 3 large dimensions: the masses of particles, the strengths of forces, the value of the cosmological constant. All of these depend on the shape and configuration of the hidden dimensions. Different shapes give rise to different physics, and there are a lot of different possible shapes. A staggeringly, inconceivably large number. The extra dimensions can be wound and twisted into configurations called Calabi-Yau manifolds, and threaded with various types of energy fields called fluxes. Each combination of geometry and flux creates a distinct set of physical laws, a different vacuum state. How many such vacuum states are there? The current estimate, first publicized by Leonard Susskind of Stanford University and others, is somewhere around 10 to the power of 500. That number is so large it defies comprehension. It is not merely astronomical. The total number of atoms in the observable universe is roughly 10 to the 80. 10 to the 500 is 10 to the 80 multiplied by itself more than 6 times. It is a number so vast that writing it out in full, with every zero, would require a sheet of paper longer than the observable universe. Susskind called this vast collection of possible vacuum states the string theory landscape, and he proposed that each vacuum state is not merely a mathematical possibility, but could correspond to an actual physical universe. If eternal inflation is constantly producing new bubble universes, and if string theory provides an enormous number of possible vacuum states, then perhaps each bubble universe settles into a different point on the landscape. Each one has its own version of physics, its own particles, its own forces. Picture the landscape as an actual landscape, a mountainous terrain stretching in hundreds of dimensions, with valleys and peaks and ridges beyond imagination. Each valley represents a stable configuration of the extra dimensions, a vacuum state. Some valleys are deep and narrow. Others are broad and shallow. The physics in each valley is different. Different particle masses, different force strengths, different cosmological constants. Now imagine a ball rolling through this landscape. It starts high up, near the peak of a mountain, in the high-energy inflationary state. As the ball rolls downhill, it eventually comes to rest in a valley. Which valley it lands in determines the physics of that particular universe. And because the landscape has 10 to the 500 valleys, there are 10 to the 500 possible sets of physical laws. In the context of eternal inflation, the picture becomes even more dramatic. Each time a new bubble universe forms, the inflation field in that bubble decays and settles into one of the landscape's valleys. Different bubbles land in different valleys. Some land in valleys where the cosmological constant is huge and positive, and those universes expand so fast that nothing can ever form. Some land in valleys where the strong force is too weak and atomic nuclei fall apart. Some land in valleys where there are not 3 large spatial dimensions, but 2 or 4 or 7. Most of these universes are sterile, empty, boring. But a tiny, tiny fraction of them, an unimaginably small slice of the whole, land in valleys where the physics is just right, where atoms are stable, where stars can burn for billions of years, where carbon and oxygen and nitrogen can form, where chemistry can become biology. And we, by definition, live in one of those rare, lucky valleys. This was a dramatic shift in how physicists thought about string theory. Originally, theorists had hoped that string theory would uniquely predict the properties of our universe, that there would be one correct configuration of the extra dimensions, and it would give rise to exactly the standard model of particle physics. The landscape destroyed that hope. Instead of one answer, there were 10 to the 500. Critics called it a catastrophe for the theory. Defenders called it a feature, not a bug, because the landscape, combined with eternal inflation, offered a potential solution to one of the deepest puzzles in all of physics. Consider the following numbers: the strength of gravity, the mass of the electron, the charge of the proton, the rate at which the universe expands, the energy density of empty space. These are the fundamental constants of nature, the numerical values that appear in our equations of physics and determine how the universe behaves. What is striking about these numbers is how precisely they seem to be calibrated. Change any one of them by even a small amount, and the universe becomes a very different place, usually a place where complex structures, and certainly life, cannot exist. Take the cosmological constant, the energy density of empty space, which drives the accelerating expansion of the universe. Its observed value is extraordinarily small, roughly 3 times 10 to the negative 122 in natural units. If it were even slightly larger, the universe would have expanded so quickly that galaxies, stars, and planets could never have formed. Matter would have been flung apart before gravity could pull it together. If it were significantly negative, the universe would have collapsed back on itself long before life could have emerged. Or consider the strong nuclear force, the force that holds atomic nuclei together. If it were just a few percent stronger, hydrogen would fuse into heavier elements so readily that no hydrogen, and therefore no water, would remain. If it were a few percent weaker, atomic nuclei larger than hydrogen could not form at all. There would be no carbon, no oxygen, no complex chemistry. The ratio of the electromagnetic force to the gravitational force is another striking example. Gravity is astonishingly weak compared to electromagnetism, roughly 10 to 36 times weaker. If gravity were even slightly stronger relative to the electromagnetic force, stars would burn through their fuel in a few million years instead of billions, leaving no time for the slow processes of biological evolution. If gravity were slightly weaker, stars might never ignite at all, and the universe would be a cold, dark void. Even the number of spatial dimensions seems to matter. In a universe with 2 spatial dimensions, complex structures are impossible because there is no room for intricate connections. In a universe with 4 or more spatial dimensions, gravitational orbits are unstable. Planets cannot maintain their paths around stars. It turns out that 3 is a very special number for spatial dimensions, and we happen to live in a universe that has exactly 3. The expansion rate of the early universe is another case. If the initial density of the universe had been just slightly higher, by 1 part in 10 to the 60, the universe would have collapsed under its own gravity before any stars could form. If it had been slightly lower, by the same tiny fraction, the universe would have expanded so quickly that matter could never have clumped together into galaxies or stars. We live in the narrow sliver between catastrophic collapse and empty dispersal. The same pattern repeats across dozens of parameters. The mass ratio of protons to electrons, the strength of the electromagnetic force, the number of spatial dimensions, all seem fine-tuned to an extraordinary degree. Change almost any one of them by a small fraction, and you get a universe that is sterile, chaotic, or simply empty. This is called the fine-tuning problem, and it has been debated intensely since at least 1973, when the physicist Brandon Carter first formulated what he called the anthropic principle at a symposium in Krakow, Poland. In its weak form, the anthropic principle says something almost trivially obvious. We observe the universe to have the properties it does because, if it did not have those properties, we would not be here to observe it. We live in a universe compatible with our existence because we could not live in one that was not. As the writer Douglas Adams put it with characteristic wit, it is like a puddle waking up one morning and thinking that the hole it sits in fits it rather neatly, and therefore must have been designed for it. But the strong form of the principle asks a deeper question. Why does such a universe exist at all? If the constants of nature could have taken any values, and if only an absurdly narrow range of values permits complex life, then why did we get lucky? The physicist Paul Davies has put the problem clearly. There is broad agreement among physicists and cosmologists that the universe is in several respects fine-tuned for life, not necessarily for human life or even carbon-based life, but for the building blocks and environments that complex structure requires. Stable atoms, long-lived stars, the chemistry of carbon, the properties of water. All of these depend on constants that appear to be set with extraordinary precision. There are really only a few possible answers. One is that there is some deeper, still undiscovered law of physics that requires the constants to take exactly the values they have. We just have not found it yet. This is the hope of many theorists, and it would be the most satisfying answer scientifically. Perhaps when we finally develop a complete theory of quantum gravity, the values of all the constants will fall out of the equations like water from a wrung cloth, leaving no room for them to be otherwise. Another is that the fine-tuning is evidence of deliberate design, that some intelligence set the dials of the universe to permit life. This is, of course, a theological answer, and most physicists are uncomfortable invoking it, though some find it compelling. The philosopher and Nobel laureate Roger Penrose has expressed sympathy for the view that the fine-tuning demands explanation, though he has not endorsed a theistic conclusion. And the third answer is the multiverse. If there are an enormous number of universes, each with different values of the fundamental constants, then it is not surprising that at least one of them has the right values for life. We find ourselves in such a universe not because it was designed for us, but because we could not exist in any of the others. It is a cosmic selection effect, like a lottery winner marveling at their luck. The odds are terrible for any individual, but if enough tickets are sold, someone has to win. This is the argument that Leonard Susskind, Andre Linde, Martin Rees, and others have made. The string theory landscape provides a vast number of possible universes. Eternal inflation provides the mechanism for actually creating them. And the anthropic principle explains why we find ourselves in this particular one. Together, they form a self-consistent picture that, whatever you think of it, is not easily dismissed. Steven Weinberg, the Nobel Prize-winning physicist, was one of the first to apply this reasoning concretely. In 1987, long before the accelerating expansion of the universe was discovered, he used anthropic arguments to predict the value of the cosmological constant, reasoning that it could not be too large or galaxies would not form, and need not be exactly zero. When, a decade later, astronomers studying distant supernovae discovered that the expansion of the universe was indeed accelerating, driven by a small but non-zero cosmological constant. Weinberg's prediction looked remarkably prescient. It was not a precise prediction, but it was in the right ballpark, and it was made before the observation. For some physicists, this was a turning point, the moment when the multiverse stopped being idle speculation and started looking like a serious scientific hypothesis. But not everyone was persuaded, and the critics had sharp objections. Before we return to the critics, there is one more version of the multiverse worth exploring, one that arises from the same string theory and M-theory framework, but takes it in a different direction. Remember that M-theory describes spacetime as having 11 dimensions. In this framework, our observable universe might exist on a three-dimensional membrane, or brane for short, floating in a higher dimensional space called the bulk. Imagine a sheet of paper hanging in a room. The paper is two-dimensional. The room is three-dimensional. Now imagine that there are other sheets of paper hanging nearby in the same room. Each sheet is a separate world, closed together in the higher dimensional bulk, but invisible to the inhabitants of any individual sheet, because the particles that make up their bodies, the light that lets them see, are confined to the surface of their own brain. In this picture, gravity is special. Unlike the other forces of nature, which are confined to the brain, gravity can leak into the bulk. This actually provides a potential explanation for one of the great mysteries of physics. why gravity is so much weaker than the other fundamental forces. Perhaps gravity is not inherently weak. Perhaps it is strong, but most of its influence dissipates into the extra dimensions, and what we feel is only the tiny residue that remains on our brain. The brain multiverse takes this idea further and asks, what if there are other brains out there in the bulk, other three-dimensional worlds floating near ours? These brains could host their own matter, their own forces, their own civilizations. They could be millimeters away from us in the higher dimensional space, and we would never know because we are stuck to our own brain. Think about that for a moment. Right now, as you listen to this, there could be an entire universe, as rich and complex as our own, hovering just a fraction of a millimeter away from you in a direction you cannot point to. A direction perpendicular to all three dimensions of the space you know. You cannot see it because light is confined to your brain. You cannot touch it because the atoms in your hand are confined to your brain. Only gravity, which is not bound to any particular brain, can communicate between these worlds, and its signal is so faint that we have not yet been able to detect it. The analogy that physicists sometimes use is a building with many floors. Each floor is a separate brain, a separate universe. The people on each floor go about their lives, completely unaware that other floors exist above and below them. They cannot see through the ceiling or the floor. They cannot hear sounds from other levels. But gravity, in this analogy, is like an elevator that can move between floors. It leaks from one brain to another. And this leakage might explain why gravity appears so much weaker than the other forces. Most of gravity's strength is dissipating into the extra dimensions, into the bulk between the brains. There is even a dramatic scenario, proposed by physicists Paul Steinhardt and Neil Turok, called the ekpyrotic model, in which our Big Bang was caused by a collision between our brain and another brain in the bulk. Picture two sheets flapping in a breeze, occasionally touching. Each touch sets off a new Big Bang on each sheet, creating a new cycle of cosmic evolution. In this view, the Big Bang was not the beginning of everything. It was just the latest in a potentially infinite series of collisions, each one creating a new universe. This ekpyrotic scenario is an alternative to inflation, not an extension of it. It replaces the idea of an explosive expansion from a singularity with the idea of a gentle collision between membranes in higher dimensional space. The word ekpyrotic comes from the ancient Greek concept of ekpyrosis, the Stoic belief that the universe is periodically destroyed and reborn in a great conflagration. It has its own set of predictions and its own problems, and it remains a minority view among cosmologists. But it illustrates the range of multiverse ideas that emerge naturally from string theory and M-theory. What all of these brain world scenarios have in common is the idea that our familiar three-dimensional space is not the whole story. It is a surface, a membrane, embedded in a larger reality that we cannot directly perceive. The matter we are made of, the light by which we see, even the forces that hold our atoms together, are all confined to this surface. Only gravity roams free, leaking into dimensions we can neither see nor touch. If you find this hard to picture, you are in good company. Even physicists struggle to visualize spaces with more than 3 dimensions. They rely on mathematical analogies and low-dimensional projections. the same way a mapmaker projects the curved surface of the Earth onto a flat sheet of paper. The extra dimensions are not out there, in any direction you can point to. They are perpendicular to all the directions you know, in a mathematical sense that has no counterpart in everyday experience. And yet the mathematics is perfectly self-consistent. The equations work. The theory hangs together. And it predicts, among many other things, the possible existence of other worlds, other brains, floating in the same higher dimensional void that we inhabit. Whether those other worlds are really out there, just a millimeter away in a direction we cannot fathom, remains one of the great open questions in physics. And then there is one more version of the multiverse, one that does not come from physics at all, but from philosophy and computer science. In 2003, a philosopher at Oxford University named Nick Bostrom published a paper that would ripple outward far beyond the halls of academia. The paper was titled, "Are You Living in a Computer Simulation?" And its argument was disarmingly simple. Bostrom started with a premise. Suppose that civilization continues to advance technologically. Suppose that, at some point in the future, perhaps centuries or millennia from now, our descendants, or some other advanced civilization, develop computers powerful enough to simulate entire universes in exquisite detail, including the conscious minds of the beings who inhabit them. These simulated beings would think, feel, and experience reality. They would believe their world was real, because from their perspective, it would be. This premise rests on a concept called substrate independence, the idea that consciousness is not tied to any particular physical material. Your thoughts and experiences are patterns of information processing. And in principle, those same patterns could run on a different substrate, like a powerful computer, rather than on the wet, carbon-based neural networks inside your skull. This is a controversial assumption, and not everyone accepts it. But it is widely shared among cognitive scientists and artificial intelligence researchers. Now, Bostrom asked, if such simulations are possible, how many of them might exist? A single advanced civilization could potentially run millions or billions of simulated universes. The computational resources required would be enormous by today's standards, but trivial by the standards of a civilization millions of years ahead of us. And if there are many advanced civilizations across cosmic history, the total number of simulated universes could vastly outnumber the single real universe. In that case, the vast majority of conscious beings who have ever existed are simulated, not real. And if you are a randomly chosen conscious being, the odds are overwhelming that you are one of the simulated ones. Bostrom did not claim that we are definitely living in a simulation. Instead, he argued that at least one of three propositions must be true. Either civilizations almost always go extinct before reaching the technological maturity needed to run simulations, or virtually all advanced civilizations choose not to run them, perhaps for ethical reasons, or because they simply lack interest. Or we are almost certainly living in a simulation right now. This trilemma has a surprising logical force. If you believe that humanity is likely to survive long enough to develop such technology, and if you believe that at least some future civilizations would be curious enough to create such simulations, then you are logically committed to the third option. The numbers are simply too overwhelming. If even a small fraction of future civilizations run ancestor simulations, the number of simulated people would dwarf the number of real ones. The idea has attracted attention from some unexpected quarters. Elon Musk has spoken publicly about taking the simulation hypothesis seriously. Neil deGrasse Tyson has said the probability might be better than 50-50, but most physicists are more cautious. The simulation hypothesis is difficult to test, and some argue it is self-undermining. If our reality is simulated, then the science we use to construct the hypothesis might also be simulated, and we have no way to trust it. The philosopher David Chalmers, known for his work on consciousness, has argued that even if we are living in a simulation, this does not make our experiences any less real. The simulated world is not an illusion, it is a genuine reality, one that happens to be running on a computational substrate rather than on the bottom-level physics of the base reality. In this view, discovering that you are in a simulation would be more like discovering a new layer of reality than discovering that your reality is fake. Still, the simulation idea underscores a theme that runs through all multiverse thinking. The possibility that the reality we perceive is not all there is. That our universe, vast and ancient as it seems to us, might be a small and provincial thing in the larger scheme of existence. So, can any of this be tested? Can we ever know if other universes exist? Or is the multiverse destined to remain forever beyond the reach of science? This is perhaps the most important question in the entire discussion, and it is the one that most divides the physics community. The honest answer is that, as of right now, there is no direct evidence for any other universe. No one has detected a signal from a parallel reality. No one has photographed a bubble universe. No one has measured the gravitational pull of a neighboring brain. The other universes, if they exist, are by definition beyond our observational horizon. But that does not mean there are no indirect avenues of investigation. Science has a long and successful history of inferring the existence of things that cannot be directly observed. From atoms, first inferred from chemical reactions long before they were seen, to dark matter, inferred from its gravitational effects on visible matter. The question is whether the multiverse can be subjected to similar indirect tests. One of the most tantalizing possibilities involves the cosmic microwave background, the afterglow of the Big Bang that fills the entire sky with faint microwave radiation. This radiation is a snapshot of the universe as it appeared roughly 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. It is, in a very real sense, the oldest photograph in existence, an image of the baby universe. The microwave background is remarkably uniform. Its temperature is the same in every direction to an accuracy of roughly 1 part in 100,000. But within that uniformity, there are tiny fluctuations, regions that are very slightly hotter or cooler than average. These fluctuations are the seeds of all the large-scale structure in the universe: the galaxies, the galaxy clusters, the cosmic web of filaments and voids that spans billions of light years. They have been measured with extraordinary precision by a series of satellites, most notably COBE in the early 90s, WMAP in the 2000s, and the European Space Agency's Planck satellite, which produced the most detailed map of the microwave background ever made. And in that map, there is something strange. In 2004, the Wilkinson Microwave Anisotropy Probe, or WMAP, detected an anomalously large and cold region in the cosmic microwave background, located in the direction of the constellation Eridanus. This feature, known as the CMB cold spot, is roughly 70 millionths of a degree colder than its surroundings, which does not sound like much until you realize that the typical temperature variations in the microwave background are only about 18 millionths of a degree. The cold spot is anomalously large and anomalously cold, and its origin remains a genuine mystery. One proposed explanation is that the cold spot is a supervoid, a vast, unusually empty region of space through which the microwave background light passes, losing a bit of energy along the way. This effect, known as the integrated Sachs-Wolf effect, could in principle produce a cold region in the microwave background. And indeed, astronomers have found some evidence for an unusually underdense region in the direction of the cold spot. But the void does not appear to be large or deep enough to fully account for the observed temperature anomaly. Another explanation, more exotic and far more provocative, is that the cold spot is a bruise left behind by a collision between our bubble universe and a neighboring one in the inflationary multiverse. If two bubbles formed close enough together in the inflating sea of space, they might have briefly collided before being swept apart by the expansion. Such a collision would send a pulse of energy rippling across our universe, a kind of cosmic shockwave, and it would leave a characteristic circular imprint on the microwave background. Some researchers have argued that the cold spot fits this description. The physicist Matthew Johnson of the Perimeter Institute in Canada has been working to develop precise, quantitative predictions for what the signatures of such a collision would look like. His team has used numerical simulations to model how bubble universes expand and interact, and they have compared the predicted signals to the actual data from WMAP and the even more precise Planck satellite. So far, no definitive detection has been made. But the search continues, and future experiments with even greater sensitivity may yet find something. It is worth pausing to appreciate how remarkable this line of research is. Scientists are actually developing methods to test the hypothesis that our universe collided with another universe. They are writing computer programs that simulate the collision of pocket cosmoses, and then comparing the results to real data gathered by satellites orbiting the Earth. Whatever the outcome, the mere fact that this work is being done represents a stunning expansion of the ambitions of science. Another avenue involves gravitational waves, the ripples in spacetime predicted by Einstein and first detected in 2015 by the LIGO observatory. If the inflationary multiverse is real, the violent processes associated with bubble formation and collision should produce gravitational waves with specific characteristics. Future gravitational wave detectors, both in space and on the ground, might be sensitive enough to detect these signals. The space-based LISA observatory, planned for launch in the coming decades, could potentially detect gravitational wave signatures from the epoch of inflation, opening a window onto the very processes that might generate other universes. There is yet another approach, one that is more subtle, but potentially quite powerful. It involves searching not for direct evidence of other universes, but for evidence that our own universe has the properties you would expect if it were one member of a vast multiverse. If the multiverse exists, and if the constants of nature vary across universes, then we should expect to find ourselves in a universe where the constants take values that are typical for life-bearing universes. This is a statistical argument, and it can be made precise. For example, if the multiverse predicts that most life-bearing universes should have a cosmological constant of a certain magnitude, and if our observed cosmological constant matches that prediction, then this counts as evidence in favor of the multiverse. There are also more theoretical arguments. If eternal inflation and the string theory landscape make predictions about the statistical properties of our universe, about the likely values of the cosmological constant, the masses of particles, the number of dimensions, then those predictions can be compared to observation. If they match, it strengthens the case for the theory. If they do not, it weakens it. This is not the same as directly observing another universe, but it is a legitimate form of scientific reasoning. After all, we cannot directly observe the interior of a black hole or the first moments of the Big Bang either, but we infer their properties from indirect evidence and the self-consistency of our theories. And yet, not everyone is convinced that this is enough. The multiverse has its critics, and their objections are serious. They come not just from outsiders or skeptics, but from within the physics community itself, from people who understand the mathematics and the arguments and still find themselves unconvinced. The most fundamental criticism is philosophical. The multiverse, at least in its more extreme forms, is not falsifiable. This is the criterion proposed by philosopher Karl Popper as the demarcation between science and non-science. A truly scientific theory must make predictions that could, in principle, be shown to be wrong. If no observation could ever disprove the existence of other universes, then the multiverse is not a scientific hypothesis at all. It is metaphysics dressed in the language of physics. This objection carries real weight. Science has always distinguished itself from other forms of inquiry by its insistence on empirical testability. You can believe whatever you like, but if you want to call it science, you have to be able to test it against the world. The multiverse seems to violate this principle in a fundamental way. You cannot visit another universe. You cannot take a measurement there. You cannot even, in most versions of the theory, receive any information from there. The other universes are sealed off from us forever. George Ellis, a South African cosmologist who collaborated with Stephen Hawking on foundational work in general relativity, has been one of the most articulate critics. He has argued that the multiverse is a speculation too far, that it invokes unobservable entities to explain observed phenomena, and that this is a slippery slope toward abandoning the empirical foundation of science. In a 2011 essay, Ellis wrote that many proponents of the multiverse do not care much about parallel universes as such. For them, the theories live or die based on internal consistency and hopefully eventual laboratory testing. But Ellis finds this unsatisfying. He insists that theories should be judged by their contact with observation, not merely by their mathematical elegance. Paul Steinhardt, who ironically helped develop both inflation and the ekpyrotic alternative, has become one of the multiverse's most vocal opponents. He argues that eternal inflation and the multiverse it produces is a sign that inflation has failed, not succeeded. The original motivation for inflation was to explain why the universe looks the way it does. But if inflation produces every possible universe, then it explains nothing, because anything can happen. A theory that predicts everything predicts nothing. Steinhardt has called this the measure problem of the multiverse in an infinite set of universes. How do you assign probabilities to anything? Without a solution to this problem, the multiverse makes no testable predictions at all. Lee Smolin, a theoretical physicist at the Perimeter Institute, has also been critical. He has proposed an alternative called cosmological natural selection, in which universes reproduce through black holes, with slight variations in their physical constants, and are subject to a kind of Darwinian selection process. Only universes whose constants are favorable for producing many black holes, and therefore many offspring universes, are common. Smolin's idea is speculative, but it has the advantage of making falsifiable predictions, which he regards as essential for any scientific theory. Others are more sanguine. Sean Carroll, a physicist at Johns Hopkins University, has argued that the multiverse should be judged not by whether we can observe other universes directly, but by whether the theory that predicts them is well supported by evidence. We believe in quarks not because we have seen them, but because the theory that includes them, quantum chromodynamics, makes accurate predictions. Similarly, if inflation and string theory are supported by evidence, and if they predict a multiverse, then we have reason to take the multiverse seriously, even if we cannot see it directly. Carroll has compared the situation to the early days of atomic theory. In the 19th century, many physicists refused to believe in atoms because they could not be directly observed. It took decades of indirect evidence before the existence of atoms was universally accepted. The debate continues, and it is far from settled. But it is worth noting that throughout the history of science, the boundaries of the observable universe have repeatedly expanded. Galaxies were once considered to be nebulae within our own Milky Way. It was not until 1924 that Edwin Hubble proved that the Andromeda Nebula was in fact a separate galaxy, millions of light years away. The cosmic microwave background was once an inconceivable abstraction. Now, it is one of the most precisely measured quantities in all of science. Black holes were once mathematical curiosities that most physicists did not believe existed. Now we have photographs of them, taken by the Event Horizon Telescope. Again and again, what was once thought to be beyond observation has eventually been brought within reach. Perhaps the multiverse will follow the same trajectory, or perhaps it will remain forever beyond the horizon, a beautiful idea that we can never confirm or deny. There is a deeper philosophical question lurking here, one that goes beyond the specifics of inflation or string theory. It is the question of what counts as a legitimate scientific explanation. For centuries, science has progressed by proposing theories that make testable predictions. But the multiverse challenges this model. If there are 10 to the 500 possible universes, and anything can happen in at least one of them, then What does the theory actually predict? How can it be wrong? Some physicists see this as a fatal flaw. Others see it as an invitation to develop new methods of reasoning, new ways of connecting theory to observation. The field of measure theory, which attempts to assign probabilities to different types of universes in the multiverse, is one such effort. It is technically difficult and philosophically fraught, but it represents a serious attempt to make the multiverse scientifically rigorous. And perhaps the most important point is this: the multiverse is not a free-floating speculation. It is a consequence of theories that were developed for entirely different reasons. Inflation was proposed to solve the flatness and horizon problems. String theory was developed to unify gravity with quantum mechanics. The many worlds interpretation was proposed to solve the measurement problem. None of these theories were invented to produce a multiverse. The multiverse fell out of them, unbidden and often unwelcome, and that, some would argue, is what makes it worth taking seriously. And so here we are, standing at the edge of everything we can know, staring into the possibility that everything we can see is just the beginning. Let us take a moment to survey the landscape of multiverses we have explored, because it is important to understand that the multiverse is not a single idea. It is a family of ideas, each arising from a different branch of physics, each with its own logic and its own implications. There is the quantum multiverse of Hugh Everett, in which every quantum measurement causes reality to branch, generating an ever-growing tree of parallel worlds, one for each possible outcome. In this multiverse, the other worlds are as real as our own, but completely inaccessible, separated by the mathematics of decoherence. There is the inflationary multiverse of Guth, Lind, and Steinhardt, in which eternal inflation generates an endless sea of bubble universes, each with its own Big Bang, its own history, and potentially its own laws of physics. In this multiverse, the other universes are not just far away. They are beyond the cosmic horizon, separated by regions of space that are expanding faster than light. There is the string landscape multiverse, in which the 10 to the 500 possible configurations of string theory's extra dimensions give rise to 10 to the 500 possible sets of physical laws. And eternal inflation populates this landscape by creating bubble universes that sample different configurations. In this multiverse, the very concept of the laws of physics becomes a local accident, a consequence of how the extra dimensions happen to be arranged in our particular pocket. There is the brain multiverse, in which our three-dimensional universe is a membrane floating in a higher dimensional bulk, possibly alongside other membranes, other worlds, just a fraction of a millimeter away in a direction we cannot perceive. And there is the simulated multiverse, in which advanced civilizations create computational copies of reality, generating vast numbers of simulated worlds within the processing architecture of their machines. These are very different ideas. They come from different areas of physics. They make different assumptions. They have different strengths and different weaknesses, but they share a common theme: the suggestion that what we call the universe may not be all there is. That reality, in its fullest sense, may be enormously, perhaps infinitely, larger than the patch we happen to inhabit. Think about what the multiverse means, if it is real. It means that somewhere, in some other branch of the quantum wave function, every decision you have ever made went the other way. Every coin you ever flipped landed on the other side. Every close call went differently. There is a version of you who took the other job, moved to the other city, said the thing you never said. Not metaphorically, actually. Or perhaps the multiverse is not about branching timelines at all. Perhaps it is about bubble universes, each one born in its own Big Bang, each one with its own laws of physics, separated from us by distances so vast that the word distance loses all meaning. In some of these universes, the constants are wrong, and nothing interesting ever forms. Just empty space, or a blinding fog of radiation, or a universe that collapses back to a point in a fraction of a second. But in others, perhaps, conditions are even more favorable than they are here. Richer chemistry, more stable stars, longer eons in which intelligence can emerge and flourish. Or perhaps the multiverse is something even stranger. Perhaps our entire reality is a sheet floating in a higher dimensional void, brushing against other sheets we can never see. Perhaps the very fabric of space and time is just one configuration among 10 to the 500 others, each one a complete set of physical laws, each one as real and as vast as our own. Or perhaps, and this is the possibility we must always hold open, perhaps there is only one universe. Perhaps the multiverse is an artifact of our mathematics, a mirage that appears when you push certain theories beyond their domain of validity. Perhaps some future theory, one we have not yet imagined, will explain the fine-tuning, explain the flatness, explain the cosmic microwave background, without invoking any universe other than this one. The physicist Sabine Hossenfelder has argued for something like this position. She has pointed out that just because a theory is mathematically self-consistent does not mean it corresponds to physical reality. The history of physics is littered with beautiful, elegant theories that turned out to be wrong. And she worries that the multiverse, by making everything possible, has removed the constraint that has always driven physics forward, the need to explain why the universe is this way and not some other way. There is wisdom in this caution. Science should be humble about the limits of its reach. The universe does not owe us an explanation that fits our preferences or our mathematical convenience. Reality is what it is, whether or not we can understand it, and whether or not it conforms to our theories. And yet, the pull of the multiverse is hard to resist, not because it is comforting. In many ways, it is the opposite, the idea that we are one of infinitely many copies, that our choices are repeated in every possible variation across an infinite expanse, that our universe is a random accident in a vast landscape of possibilities. None of this is designed to make us feel special or significant. If anything, the multiverse is the ultimate Copernican revolution, pushing us not just from the center of the solar system or the center of the galaxy, but from the center of reality itself. And perhaps that is exactly why it matters. Because the greatest discoveries in the history of science have always been the ones that made us smaller. Copernicus showed us that Earth is not the center of the universe. Darwin showed us that humans are not separate from the rest of life. Hubble showed us that our galaxy is not the only one. Each of these revelations was disturbing, even painful, and each one made us wiser. If the multiverse is real, it would be the most profound of all these revelations. It would mean that not just our planet, not just our solar system, not just our galaxy, but our entire universe is a small and unremarkable thing in the grand scheme of existence. It would mean that the laws of physics themselves are local and contingent, not universal and necessary. It would mean that the question, why is the universe this way, has no deeper answer than because, in an infinite set of possibilities, some universe had to be. We do not know, and that is the honest truth. We do not know if we are alone, the only pocket of reality in an otherwise empty void, or if we are one among an infinity of worlds, each as real as our own, each home to its own story. But what we do know is this: the question is no longer the province of philosophers and poets. It has entered the domain of physics, of mathematics, of observation and experiment. Real scientists at real institutions are working on this problem right now. They are building detectors, running simulations, developing theories, arguing fiercely about what is possible and what is not. The question of other universes has gone from wild speculation to a research program. The scientific journalist Tom Siegfried, whose book The Number of the Heavens traces the history of multiverse thinking from ancient Greece to the present day, has put it well. He has argued that we cannot explain all the features of our universe if there is only one of them. The patterns we see, the constants we measure, the structures that have emerged over billions of years, all of these seem to demand a larger context. Perhaps that context is the multiverse. Or perhaps it is something else entirely, something we have not yet conceived. What is certain is that the question itself has proved remarkably persistent in every era of human civilization, from the pre-Socratics to the Renaissance to the 21st century. Someone has stood up and asked whether our world is the only one. The tools have changed, from philosophical arguments to telescopes to particle accelerators to satellite observatories. But the fundamental impulse is the same. It is the impulse to look beyond the horizon, to ask what lies on the other side, to refuse to accept the boundary of the known as the boundary of the real. And that, more than any answer, is what matters. Because the willingness to ask the biggest possible questions, to follow the evidence wherever it leads, even if it leads to places that make us uncomfortable or confused, that is what science is. That is what it has always been. Giordano Bruno was burned alive for daring to imagine what lay beyond the visible sky. He stood in that Roman square, facing death, and refused to recant his vision of an infinite cosmos teeming with worlds. He could not prove his ideas. He had no telescope, no equations, no data. He had only his conviction that the universe was far larger and stranger than anyone around him was willing to accept. 4 centuries later, we have instruments that can peer back to the first 380,000 years after the Big Bang. We have mathematics that describes the quantum behavior of individual atoms. We have theories that reach into 10 or 11 dimensions of space. And still, the deepest question remains the same one Bruno asked, the same one human beings have asked since they first looked up at the stars. Are we alone? Is this all there is? Or is reality far, far bigger than we ever dared to imagine? We may not have the answer yet, but the fact that we are asking, the fact that we can ask, and that we have the tools to begin searching for the truth, That by itself is a kind of miracle. There is one final thought worth leaving you with. Max Tegmark, the Swedish-American physicist who has developed one of the most comprehensive classifications of multiverse types, has pointed out something profound. He calls it the mathematical universe hypothesis. Tegmark suggests that every mathematically consistent structure exists physically somewhere. If a set of equations describes a self-consistent universe, then that universe is real. The physical world is not merely described by mathematics. It is mathematics. If Tegmark is right, then reality is not just bigger than we thought. It is everything that could possibly be, every consistent set of physical laws, every possible arrangement of matter and energy, every story that does not violate the laws of logic. All of it exists. We are not just one universe among many. We are one equation among all equations, one solution among all solutions, one story among all stories. It is an idea that is either the ultimate expression of scientific humility, the recognition that we are a tiny part of a vast mathematical reality, or the ultimate expression of scientific hubris, the claim that we can deduce the structure of all reality from equations on a blackboard. Probably it is both. But whatever the truth turns out to be, whether we live in one universe or many, whether reality is a single thread or an infinite web of possibilities, the journey of discovery itself is something to treasure. The fact that a species of primates, living on a small rocky planet orbiting an ordinary star in the suburbs of an unremarkable galaxy, has managed to ask these questions at all. That is the greatest miracle of them all, from Democritus, dreaming of infinite worlds in ancient Greece, to Giordano Bruno, burning alive for daring to imagine them, to Erwin Schrödinger, writing equations that describe a cat that is both alive and dead, to Hugh Everett, a lonely graduate student who saw that math implied infinite branching realities, to Alan Guth, realizing that inflation might never stop, to Leonard Susskind, surveying the landscape of 10 to the 500 possible universes, to the engineers and scientists building detectors and satellites, searching the microwave sky for the fingerprints of other worlds. The story of the multiverse is a human story. It is a story about curiosity, about courage, about the willingness to follow an idea wherever it leads, even into places that make us dizzy, even into territory that challenges everything we thought we knew. You have been watching, and we are glad you stayed with us for the journey. If this video gave you something to think about, if it sparked a sense of wonder or curiosity, please consider hitting the like button and subscribing to the channel. Leave a comment and tell us what you think. Do you believe the multiverse is real? Or do you think there is only one universe, and it is the one we are living in right now? We would love to hear from you. Thanks for watching, and we will see you next time.